So talk number 3 for today is Triangulated Categories of Log Motives over a Field, Part 2 by Frederico Binda.
Okay, thank you, Mark, and thank you very much for the invitation. It's really nice to be to give a talk in this conference. Unfortunately, it would be much nicer if we could be all together in Oslo, but well, you know, it's not going to happen. Okay, so as Mark said, this is the second part of yesterday's talk by Thom. I mean, it's not strictly speaking necessary to have listened to the talk yesterday for understanding what I'm going to say, because I will give at least some recollection. And let me just say that this is all joined with Thom and Paul Arne. Okay, so let me start with some recollection from yesterday. Well, so what was our starting point? So the starting point for various reasons was to compactify smooth schemes. And well, if you do it in a nice way, then you get nice log schemes. So ideally, which means, for example, if you have a solution of singularities on your base field, so everything will be, okay, so let's say we are over, everything is over a field K. At some point, I will assume K to have a resolution of singularities. But anyway, so well, let's assume that we have at least a good compactification of our scheme X. So X is smooth over K. And for the moment, let me also assume that the compactification is smooth. And the complement is strict normal crossing divisor. Okay. So in coordinates, this means that we pick up a point in our divisor, D, and we have local parameters, say T1, TD, and the divisor is the zero locus of, say, T1, TR. And well, the log structure, so lucky for me, Piotr Ackinger yesterday also gave a short introduction of a terminology in log geometry, so you don't have to repeat much here. So let me just say that this is the standard way we produce log structures out of this specific geometric situation, which is the situation mostly interesting for us. So we have a morphism of monoids from N to the R to the sheaf of monoids of OX bar. So we see this guy as a multiplicative monoid, and we send A1 to AR, so tuple of integers, to T1 to A1, TR to AR. And some people call this a Lehm-Faltings log structure, or a compactifying log structure, anyway. So the pair, Y, that we consider here, so is X, say X bar, comma D, gives a log scheme. And I would like to stress that the datum of a log scheme is a bit more than just giving the divisor, okay? So that's because of the choice of a log structure. So for example, I could have done something silly. So I could have taken, instead of N to the R, if R are the components of my divisor, I could have taken just N. And instead of sending A1, AR to this product, I could just say, well, let's send A to, so for example, something like A goes to T1 to the A, TR to the A, okay? This will be a different log structure, and that's not the log structure that we want to consider. So really consider all the components separately. Okay, anyway, so the pair, we will denote the pair in this way, and the underline, as Piotr was saying yesterday, will mean, well, the underlying scheme of our log scheme. So in my baby example here is just X bar. Okay, so, and as an example, so the thing we want to keep in mind is what Thom was saying yesterday. So we start from the affine line A1, and we choose this compactification. Well, there is only one, so there's not much to choose, which is given by P1 and the divisor at infinity, okay? And that's our replacement for A1 to build motives. Okay. Then let's consider this following picture. So how do we pass from a bunch of ingredients to motives? So in algebraic geometry, we have a base, we have a category of varieties. So like say smooth schemes over K, or smooth schemes over any reasonable scheme S, or the category of correspondences. In Voevodksky's word, we consider the interval the affine line A1. The topology is either Voevodksy or Misnevich or étale topology, different purposes. And the resulting gadget that we get if you localize respect to A1 and respect to the topology is the category of motifs, like DM or DA, according if you consider with or without transfers. So in our log setting, with our base, at least for the moment, will be K, the field without any log structure. So let's say K triv, but I will forget to write triv, so we'll just write K. Okay, so maybe towards the end of the talk, I will make some comment on what happens if you allow a non-trivial log structure on the base field. And the category of varieties is replaced by so smooth over K is replaced by log smooth over K, or category of log correspondences, also introduced by Gysin yesterday. I already said something about the interval, and the topology will be, well, the dividing Misnevich or étale or variants of this. Okay. All right. So once we do have this the setting, we can consider. So we have a topology, and we have a category of schemes. We can consider pre-sheaves with values in, say, lambda modulus. So lambda is some coefficient ring. This will be if we start from correspondences, we call this pre-sheaves with log transfers. Okay, that's the LTR on top of the pre-sheaf on the left. And important theorem in the story is that if you consider the sheavification with respect to the dividing Misnevich topology, then this behaves well with respect to the transfer structure. So this respects transfers. Okay, then, so in order to prove this, we use this generalization of Voevodksky's result on CD structures. And for example, this needs to be extended to the notion of quasi-bounded CD structure. This is also mentioned by Gysin yesterday. Okay, let me make a couple of remarks. First one is that you can consider the Yoneda embedding of log correspondences into pre-sheaves with log transfers, and you can quickly check somehow that this is not a dividing Misnevich sheaf. It's not so surprising, because if you remember, the dividing topology involves considering certain kind of blow-ups. Okay, so this log modifications, as Gysin said yesterday, and well, this is not quite the same as the CDH topology, but you know, it's already not the case that the CDH topology is subcanonical. So if you have blow-ups here and there, then it's not surprising that the representable pre-sheaf is not a sheaf. Okay, but somehow it's interesting to compute the sections of the dividing Misnevich sheafification of Z log transfer of X, so using Yoneda guy, and this is what it is. Well, roughly speaking, this is given by finite correspondences, okay? Finite. Well, no, sorry, simply correspondences rather than finite. So let's say correspondences, which are not finite, but W becomes finite after also over X, okay, after a log blow up or a log modification. Okay, so if you are familiar a bit with a construction by Miyazaki and Kahn on topologies of modulus pairs, then you will see some similarities here, okay? So the condition that in the topology, you don't achieve finiteness directly on the correspondences, and this is somehow interesting to keep in mind, because at first sight, our restriction, so the kind of correspondences that we consider is a fairly small class, because we require the correspondence to be finite everywhere, so not just on the complement of a boundary of a log structure, but somehow this is sort of corrected by means of a topology. Okay, so thanks to the dividing Misnevich topology, you can sort of relax this condition a bit, and then you can sort of play with sections of this Yoneda guy and get correspondences which become finite only after some blow up, okay? In a very controlled way. So because these log modifications are really like, well, somehow you're allowed only to blow up strata of your device, okay? Not random things. So this is the first remark I wanted to make about this category of sheaves. And the second one is that we have a theorem that allows you to compute the cohomology, the dividing Misnevich cohomology of any bounded complex of dividing Misnevich sheaves. And at least when X is smooth log smooth, so that's yesterday's notation by Thom. And you can compute it in terms of colimit of the strict Misnevich topology, so somehow the topology which sees very little about the log structure, and you have to take colimit over all y's over X. So these are all the log modifications such that Y is smooth. Okay, and you can use this theorem somehow to extend also your definition. So in a way, if you know how to define cohomology theory, for example, on smooth log smooth things, then you can extend it to all log smooth things by taking this kind of Kahn extension via log modifications. Okay, so this was some of the things were already discussed yesterday, some not. But now anyway, we are ready to redefine our category of motives. So we start from the category of dividing Misnevich sheaves with log transfers. And we have said that, well, take the localization with respect to this box guy, and you get logDM in is K lambda, okay? And we have this nice commutative diagram. So here we have a usual category of sheaves with transfers on the big Misnevich side on smooth schemes over K. And if you take A1 localization, you get DM. And this functor omega upper star is the functor induced on sheaves by the functor sending log scheme X to the complement of a divisor, okay, of a log structure. Or if you want to be more precise, you send a log scheme X to the open subscheme consisting of points where the log structure is trivial. Okay, so this was so much for a summary. So if you have questions, please do interrupt me. And now I would like to discuss some properties of this category, okay, and discuss some results, some structural results, and then some nice theorems that we could prove using this formalism. Okay, so let me denote as usual by M of X the motive of X. So that's the image in logDM of the dividing Misnevich of the pre-sheaf with transfers lambda LTR of X. So it's an almost immediate consequence of the construction that this category logDM inherits a monadal structure, that you have Mayer-Vettori squares for strict Misnevich covers, and that you have dividing invariance. So yesterday, Thom discussed how you get from box invariance this Pn minus one invariance. Okay? So you can interpret this result by saying that in our category, every smooth compactification of AN is inverted and is equivalent to a point. Okay, so rather than starting from A1 and you compactify to P1 and then to P1 with boundary infinity, when you contract X times this guy or X times this guy to the N, you could also contract this Pn minus one, which is yet another compactification of AN, or any other smooth compactification of AN with log structure given by a boundary, so you can blow up as much as you like, and you will still not change the motive, okay? So, so we also have blow-up triangles, and let me put this in parentheses because I will discuss them probably maybe later if I have time, but
Federico, there's a question. Does this functor W star have an adjoint left or right adjoint?
Yes.
Yes.
Both.
Oh, okay. Thanks.
Yeah. So, but I mean, this is yeah. So, for example, I mean, yeah, it's a yeah. So the left adjoint is let me see. Yeah. So you have both adjoints. I mean, they come from the general nonsense. I mean, you have a restriction factor on the category of schemes, and then you get the left and right Kahn extension, and then you show with this they are compatible with localization. Okay, but I will say something about this one of the adjoints later when sort of writing down explicitly what the comparison results between DM and logDM. Okay, so okay, so right, so we're saying that we also have Thom space isomorphisms and Gysin triangles. Okay. So I will come back to this later, but first let me say something about the comparison with Voevodksky's motives. Okay. So let's assume that K has a resolution of singularities, and that let's take say X and Y log smooth over K, and let me assume, moreover, that X underline is proper over K. This is really crucial. Okay. Then you can compare the Thom, and that's probably Ran's question, or will answer to Ran's question. You can compare the Thom in logDM between the motive of Y shifted I and the motive of X, and the Thom in DM between the corresponding motives of the complement of a log structure. So say that the partial X and partial Y denote the set of points where the log structure is not trivial. And we have an isomorphism like this. Yeah? And as a consequence of this, you get the adjunction is between logDM and the DM is actually a localization. So this omega upper star is fully faithful, and we can identify DM effective Nisnevich inside logDM as follows. So it's the same as the category of complexes, so objects in logDM, such that K is A1 local. Okay, or maybe I can also say strictly E1 invariant complexes. So I think this answers to a question that Chuck Bible asked yesterday about, well, how do you get back cohomology theories of type 1 in Duzong's lecture? That's, well, in DM, that's the precise result that we have. Okay, so you need to assume resolution of singularities, and that's because we have a it's a technical condition. I mean, it appears in the cofinality construction of the colimit that I wrote before, and for computing dividing Nisnevich cohomology. But anyway, so all right, so that's how you identify DM, and that's at least one way you identify DM. The second way to identify DM inside logDM is the following. So let's consider the subcategory in logDM generated by M of X such that X underline is proper. Okay, and another result is that this actually also gives you back DM. So here, two remarks. The first remark is that this is not exhaustive. So the category logDM is not generated by the motive of proper varieties, M of X. That's because we don't have a localization sequence as you do have in DM. Okay, so there is still room for something between logDM and logDM proper. For example, the motive of A1 is in logDM, is not in logDM proper, which is good because our theorem claims that logDM proper is equivalent to DM, and the motive of A1 is a bit boring in DM. Okay, so that's one thing. And the other thing is that, and here I stressed by using the color pink, is that this is true for the Nisnevich topology. Okay, so if this is true, and here we have Diniz. So this also doesn't hold in the étale setting, for example. So I will say something more on the étale topology in a second. Okay, so now when you have such a comparison with DM, you can inherit a number of results. So for example, the projective bundle formula and a version of a blow-off formula.
Can I ask a quick question?
Sure.
So can I think about this last isomorphism as saying you have an open variety, you take a smooth projective compactification and give it the log structure by taking, with normal crossing divisor at infinity, and that's how you should think of this thing as a log motive.
Correct, yes.
Great.
And the motive of the original variety is precisely, in DM is sent to the motive, in this equivalence is sent to the motive of this pair. Okay.
Great, thanks. Yeah.
So exactly. Yeah. So this is precisely what happens. Okay. And of course, if you don't compactify, so if you take only the motive of something open and then you don't put any log structure, then this is still an object that you can consider in logDM, but it doesn't come from DM. Okay. Good. So so on the same line, so let me stress what is the difference between logDM and DM then, because that's a reasonable question, and that Mark asked me before. So let me answer it properly this time. So what is the difference between logDM and DM? And let me make this example, and so I can say the following theorem. So you can consider the sheaves omega j blank over k. So this is the sheaf of log differentials. So a priori this is defined on log smooth over k, well, even on a bigger side, but okay, it doesn't matter. And okay, so theorem says that these are strictly P1 infinity invariant Diniz sheaves with log transfers. Okay, so the transfer structure, which is really the tricky part here, actually comes from the work of Andre Casita-Mathieu and Kai Ruling, who proved in sort of in the generality that we needed, that you have a correspondence action on the sheaves of differentials. There is also in characteristic 0 a different construction of transfer structure of the differentials, but doesn't really doesn't really work for our purposes. So once you do have this theorem, and of course you can say that these guys, so these omega j's, are motives. Okay, so are objects in logDM, and for which you can compute the cohomology. Okay? So let me quickly say what are the ingredients to go into the proof of this theorem. So for the P1 invariance, so the P1 infinity invariance, and the fact that this is preserved by the cohomology, by thinning cohomology, what you use is the P1 boundary formula for the differentials, okay? which is classical, but still you need to have it. For the dividing invariance, the observation here is that dividing covers are a proper log étale monomorphism. So in particular, log étale maps. And log étale, well, if you forget about the log and you focus on the étale word, then you can sort of believe that étale maps don't change the differentials. So this is another thing. And the correspondence action that I was briefly mentioning before, well, it follows from like a careful analysis of some growth individuality for coherent sheaves, and that you need to construct the push forward. So that's what you I mean, at the end of the day, this is what you need to get the correspondence actions. Okay. Anyway, once you put all these things together, then you have the following corollary, that the cohomology, and here cohomology you can take your favorite topology, so they're all equivalent. So the Diniz, but also Zariski or Nisnevich of of x underlined with coefficients in omega j x over k. So here, like, pay attention to the notation. So there is an x underline as a space, so that's the scheme, and x without the underline is the log scheme. So explicitly, this would be omega j x underline log boundary of x, okay, over k. And okay, so as a consequence of our theorem, that this is the same Thom in logDM between the motive of x and omega j k brackets I. Okay, this is for I and j greater or equal to 0. And this in particular shows that logDM is not the same as dm, right? Because this is not true. The Hodge homology is not representable in dm. And in characteristic 0, you can use HKR, so Hochschild-Kostanter-Rosenberg theorem, to get a formula for cyclic plus like standard descent techniques, to get a formula for cyclic homology of x. Okay, so which is also just Thom in logDM between motive of x and the direct sum of these guys. Okay, so here so it's hc over k, and this is also over k. So you could also use the right formula, so Thom in logDM between m of x into this gadget, to define cyclic homology for log schemes. So x doesn't have to be, so here, for example, x could be a smooth scheme over k, but also, so with trivial log structure, but also x in log smooth over k. So this gives you a definition of a logarithmic cyclic homology. And since people already defined logarithmic cyclic homology before, then question is, well, is this the same notion, or are you producing a different gadget? The answer seems to be, well, yes, they are the same. And this relies on some unpublished results by John Rognes. And somehow, well, this is probably, so in a way you need a log version of the Hochschild-Kostanter-Rosenberg theorem, which doesn't seem to be written down in the literature, but seems to be true. So you can use this as to compare log cyclic homology sort of independently defined with this formula. Okay, so then I promised something on the étale story, on the étale side, okay? So let's think a bit about what is the replacement of the étale topology in this setting. So the first attempt is, well, let's do the same thing as we did in the Isnevich case. So let's consider the dividing étale topology. So what it is, well, you take the dividing covers, which we like very much. So dividing covers, and plus strict étale covers. So remember that strict étale means that's étale, okay, as a morphism of the underlying schemes, and that the source has a log structure which is induced by the target. So if you think in terms of schemes with compactifications, it means that you have an étale map of a global guy, and that the divisor that you consider on the cover is the pullback of a divisor that you have downstairs. Okay, so that's sort of simplest possible situation. Okay, but on the other hand, this is not quite the correct thing to do to consider in this setting. So let me explain why. So let's consider the Kummer sequence in the log setting. So here you can okay, so you can consider the sheaf M group. So M group, I wrote it here on the right. So since T a log scheme to the global sections, so gamma T of M group restricted to T. So this is a group completion of the monoid associated to T. So giving you a log structure on T. If you restrict yourselves to log smooth schemes with compactifying log structures, which is exactly what we are considering here, then this gadget is not so exotic, it's just GM. Okay, so the sections on the log scheme just be the sections of GM on the open complement of the boundary. Okay, and so it's not so, well, it's not so scary. But the important thing to remember is that this thing is not exact for the dividing étale topology, which is a bit annoying. So let me explain why. So this boils down to be a local question, right? So if I pick up a section, say on X on my M, then the question is this guy, is this nth power, right? So my A can be interpreted as a map from X to a N, like N below here. So this is the, for example, is an avatar for GM, right? So something like N to A1, so and sending N to T to the N, okay? That's a log scheme. And so a section of M is the same as a map from X to AN, and then you can consider the map from AN to EN given by T mapping to T to the N. And this is not an étale map on A1, right? So because on 0 you have ramification. So this is not a strict étale cover. And it's also not a blow up, so it's also not dividing cover. So, but these kind of maps, luckily for us, have been studied before. So these are the kind of maps that are called Kummer étale maps. As long as n, say p is equal to 1, where p is the exponential characteristic of k. Okay, so then we can consider the Kummer étale topology. So topology, that's the topology generated by Kummer étale covers, and the log étale topology, which brings back dividing covers in our picture. Okay, so if we consider the log étale topology or the Kummer étale topology, then the Kummer sequence becomes exact, which is something that we are happy with. Okay, so then we can define as expected logDM for the dividing étale topology and for the new log étale topology that I just discussed. And well, a natural question is let's see what happens if we take torsion coefficients, okay, in this étale word. So let's say that lambda is a torsion ring, and let's work coprime to the characteristic, to the characteristic of K, and so our result in this direction is the following. So every locally constant log étale sheaf on log smooth over K admits a unique transfer structure. So in the non-log setting, this is a theorem of Suslin and Voevodksy. So as a corollary, so we get a fully faithful functor so eta sharp from the derived category of sheaves on the small side of K, so étale side of K with lambda coefficients, to logDM with the log étale topology. Okay, and this is induced by the change of side functors, right, from the small side to the big side. So notice that there is no, so I wrote K at and not K let log étale because there are no, well, there are no log modifications on the small side of K, right? I mean, K is just a field, so there's not much going on apart from étale covers of the field itself. Okay? So this is really the usual guy, okay? Usually derived category of sheaves on the small side. And the more exotic thing is this logDM. Okay, so then we decided to make this conjecture. So we call it log Susan rigidity, and the conjecture is that this eta sharp is an equivalence. So So why do we believe in this conjecture? Well, essentially because since we are working with torsion coefficients prime to the characteristic, then we don't think that there are known A1 invariant phenomena that we can capture with logDM. So in a way, we don't expect logDM to be different from actual DM in the étale setting with torsion coefficients prime to the characteristic of K. Okay, so an equivalent formulation of this conjecture is that every prime to P torsion is strictly cube invariant log étale sheaf, that's very long to say, is locally constant. Okay? And let me stress here that I have to say strictly box invariant sheaves, because there are examples of box invariant sheaves which are not strictly box invariant sheaves. So for example, mu_n, okay? If you consider, for example, if you compute the strict étale cohomology of mu_n on the box, this is the same as the cohomology of P1 with mu_n coefficients, and that's not is not isomorphic in general to the cohomology of spec K. So this is so for example, if K contains all the n root of unity, then Z mod n is not a strictly cube invariant sheaf for the strict étale topology. So one has to be a bit careful, and to safely say the conjecture, we have to restrict ourselves to the strictly cube invariant sheaves. Okay, so questions on this? Otherwise, let me.
What goes wrong with Susslin's proof?
What goes wrong with Susslin's proof? He uses the Picard group.
And you'd have to replace that. What would the replacement?
Yeah, well,
Okay.
that proof doesn't quite work. I mean,
good.
Yeah. So I don't know. So one is probably to come up with a different argument for this. Okay, so since I said something about the torsion prime to the characteristic, let me say something about the case of torsion at the characteristic. So let's say that we are in characteristic P and that we consider Z mod P coefficients. Okay. So so that's actually a much better situation, because if you take Z mod P coefficients, then well, this guy, so the sequence, like the usual Artin-Schreier sequence, is actually exact for the étale topology, or the strict étale topology on log smooth over K. So there's no funny thing happening here. So there is no we don't need to go to the Kummer étale site to get something exact. Okay, which is good. And now you can consider logDM effective with respect to the étale, say, dividing étale topology, okay? And well, this thing is not zero, right? So why do I say that, why do I worry, why am I worried that this thing is zero? Because recall that if you take instead DM étale K Z mod P, then the same Artin-Schreier sequence shows that this category is trivial, okay? Because GA is contractible in DM, so Z mod P better be contractible, well, better be zero, and if you take Z mod P coefficients, well, so sort of you're killing everything, okay? So to put things differently, DM étale over K, and K is characteristic P, is automatically Z1 over P linear as a category. But in our setting, this is not the case. So for example, you can commute Thom from M of X to Z mod P and logDM étale, and this is the same as H0 of X underline with coefficients in Z mod P, and that's not zero in general. So this is this category. In this category, you have gadget like Z mod P, okay, which survives and is actually lives in the subcategory, and this is what I'm writing here. This guy actually lives in the subcategory generated by proper things. Okay, so Z mod P is proper. Z mod P to VR is proper, right? Is given by the motive of spec K in Z mod P to VR coefficients. So this also shows the difference between the Nisnevich setting and the étale setting. Remember, before I said that in the Nisnevich setting, logDM Diniz prop was giving you another incarnation of DM, and this is not the case in the étale setting. Okay, also, yeah. So the question, since we do have this nice Z mod P to VR guy here, is if we can use this category to get an integral log crystalline realization. This would be somehow a refinement of the rigid realization from DM et al. With QP coefficients, okay? And would fit in, at least conjecturally, would fit in the same square, but Milne and Ramachandran considering the category of étale motivic complexes. Okay, so what do I mean by integral log crystalline realization? So I would like to have a functor, let me call it R Chris, to the bounded category of coherent complexes, C mod P to VR coefficients, over of graded R modules, and R is the Raynaud Dieudonné ring. Okay. So it's okay. So this is a sort of technical thing. I mean, it's not so important to discuss the details. But if you say if I pass from Z mod P to VR to ZP and then I invert P, then so this is like I'm working with finite coefficients. Okay, Z mod P to VR. So let's say that I work, just to give you an intuition of this category, DBCR, Z mod P to VR. If I work with ZP coefficients and I invert P, then I get the bounded derived category of complexes of like K modules, where K is the fraction field of the Witt vectors of your ground field. Those homology groups are F isocrystals. Okay, so okay, it's a fairly studied object, and this would be the target of what we would like to have as a crystalline realization. So if you have such a map, then you can actually compare, and you have it for every R. You could compare this with the rigid realization. Okay, so let's just say that in DM et al. Over K Z1 over P, you have something going to D K sigma F, and this sends X to R gamma X over K. This is sort of rigid homology. Okay, so this is all very conjectural. Okay, so this is a speculation. We would like to have such a thing, and we have some hope, at least because the source is not stupid, right? And actually, in the source, you have something like truncated Ramwitt sheaves. All right. So if you don't have questions on this, then I will move on to a different topic. And for the rest of my talk, I will discuss two more things, which are Thom spaces and Gysin maps in our setting. Okay. I will go on. I will go on. Okay. So okay. So let's go back to Nisnevich. So back to log DM Diniz. Okay. Lambda. Also still effective. Okay. So let's remind ourselves that in A1 invariant motivic categories, for every vector bundle E over, say, scheme X, we can define the motive of the Thom space of A over X as the, so let me use this notation. So the motive of E minus the zero section to the motive of E, okay? So this means the co-fiber or cone in this triangulated category. So what happens in the log setting? So first of all, let me introduce a bit of notation. So if say x is equal to x underline d with usual story, so x is smooth log smooth and d is a SNCD on x underline, and let's say that we have a vector bundle on x underline with projection pi from e to x underline, and let's consider this e curly e as a log scheme, having underlying scheme the vector bundle e, and as log structure, the log structure induced by the pullback of a divisor. Okay, so from x underline to e. So let's consider the zero section of this vector bundle, and let me write BZE for the following log scheme. So I consider the blow up of the zero section of the scheme E, and as a log structure, I consider P upper star of pi upper star of D plus the, say, let's call this guy F, okay, plus the exceptional divisor. Okay, so now I have a map back to X, well, back to E, sorry, here. And so let me give the following exotic definition. So the motive of the Thom space of this E will be motive of this blow up to E. Okay, I call this Thom motive. Okay, so that's a definition. And well, why is this a reasonable definition? So let me make a quick topological justification. Okay, so if, for example, X is equal to spec K and E is just a trivial bundle, then Z, the zero section, is just 0 inside AN. So let's say that we are in characteristic 0, for example. So this BZE is the blow up of AN at the origin, and there is no log structure here, so there was no log structure on X, so we only have the exceptional guy, the exceptional divisor, as a boundary. And I can consider the Bethe realization of this log scheme. This gives the Kato-Nakayama space that Thom was mentioning yesterday in his talk. And in this case, this happens to be the same thing as S2n minus 1, like a sphere. So this has a natural map to AN with trivial log structure. So because it's a map induced by the projection of the blow up, okay? And if you take the Bethe realization of this thing, you just get a disk, D2n. So the motive, the Bethe realization of the Thom motive of AN in our log setting is the same thing as a disk bundle modulo a sphere bundle, which is the topological Thom space, like this is a sphere dimension 2n. Okay, so the homotopy type of our Thom space or Thom motive is the correct one. Okay, and somehow the idea in the story is that, well, since we are not allowed to really take the complement, so what goes wrong in a way, right? Let's go back to this slide. So what goes wrong in this definition? The problem is that in the classical definition, we take the complement of a zero section, okay? And the slogan is that you're not allowed to take open guys in the log setting, naively. So this E minus Z, so this complement of a zero section should be rather replaced by the pair E comma Z, but well, Z is not a divisor, so this is not really a log scheme. So what you do, well, you blow up so that you get a divisor, and this gives you a log scheme. Okay, so that's the idea. And okay, so let me go back to this slide. And for example, you can okay, now that you have this definition, then you can compute this Thom space in nice cases. So for example, the Thom space of E over X is just the same thing as this cone, the motive of a projective bundle over E to the projective bundle of E plus a trivial summand. And in particular, this gives you that motive of over X of, say, something like X times A1 is what you expect. So M of X, twist 1 So Tate twist 1, shift 2. Okay, so as an application of this Thom space construction, I can now discuss Gysin maps in our setting. Okay, and here the sort of sign of attention is the same as I was briefly mentioning before. Okay, so we don't have a Gysin isomorphism as in DM. So the Gysin isomorphism in DM would be the motive of x minus z into x, say that z is move of codimension c, is the same as the motive of z twist c, shift 2c. Okay, this we don't have. And the point is that we really need to compactify this x minus z to actually get a proper formulation. Okay, and because this x minus z otherwise is not really a gadget that we can handle in our logarithmic setting. So you can guess what we do. So how? Well, we have to replace x minus z with the blow-up, bzx e. Okay? Even if x and z have trivial log structure. So this is like a non-trivial operation, even if you consider schemes, like usual schemes seen as a log scheme with trivial log structure. Okay, and our theorem is that there is a natural isomorphism in logDM, which we call the Gysin map, from the motive of this gadget, which replaces x minus z to x, and the motive of the Thom motive of x, of a normal bundle of z in x. Okay, and if you, well, maybe this is an important remark, but if you take A1 localization of this thing, so if you pass from logDM to DM, thanks to the functor that I mentioned a few slides ago, this gives back the usual Gysin isomorphism that, for example, was discussed by Frederico in many of his papers. So how do you prove such a thing? Well, the tool is, how do you prove a Gysin isomorphism in general? You use the deformation to the normal bundle. So you have to find an analog or reasonable generalization of a deformation to the normal bundle picture to the log setting. So let me quickly say what is the kind of diagram that you have to look at. So, and for simplicity, let me restrict to the case where, well, to begin with, let's say that x doesn't have a log structure. So just to begin. So x is a smooth scheme over k, and z inside x is smooth, say of codimension c. Okay, so both smooth. And let's write dz for dzx for the affine deformation space. So this is exactly what you do. It's exactly the same thing as what you do in general. So you take the blow up of z times 0 in x times box. That's what instead of x times a1. This is what you would do in DM, right? And you remove the trivial factor bzx. And then you can form the following diagram. So let's say that we have z1, zr strict normal crossing divisors on our x. And let's make this further, this extra assumption that z has S and C with z1, zr. So this means that if you restrict z1, zr to z, you get a strict normal crossing divisor on the smooth variety z. Let y be the log scheme given by x with boundary z1, zr. And let's consider this, this picture. So at the center here, we have, so here we have this affine deformation space. This is it's a bundle over box. You have a fiber at 1 and fiber at 0. The fiber at 1 is y. The fiber at 0 is the normal bundle of z and y. So far, so good. But on top of that, instead of considering the z and the normal bundle of z, well, you consider the blow up of y at z. So this bzx with exceptional divisor as a log structure, and you add this exceptional guy. You add this guy. EE is the exceptional. And same thing in the middle, you take the blow up of z times box in dzy, and you have an exceptional guy. And here you take the blow up of z in the normal bundle, and you take the, so it's a 0 section, and you take the exceptional. Okay, then the Gysin isomorphism boils down to to the following, to studying the following maps or the following zigzag. So notice that if you take the cone of this map here, so this is what I wrote on the right, this is exactly the definition of the motive of the Thom space, okay, that I gave in the previous slide. So here you have on the left the replacement of the cone of the map from the open complement of z in y to y. And then you have in the middle this deformation space, which interpolates between the two. And then, of course, what you have to show is that these maps are equivalencies. Right? Then the proof goes more or less parallel to what happens in the A1 setting. It's a combinatorial at some point when you have to do some toric game, okay, as Duzong, more or less the kind of thing that Duzong was explaining yesterday for comparing P2, P1 to P1 times P1. Okay, so I have few more minutes, and I want to use the last 5 minutes to explain another connection, also a connection of our theory to another theory that aims at understanding a known homotopy invariant phenomena. So that's the category of, that's the theory of reciprocity sheaves. Okay, so inside the usual category of sheaves with transfers on Nisnevich sheaves with transfers on smooth schemes over K, one has this category, this abelian category of reciprocity sheaves studied by Kahn-Saito-Yamazaki. Okay, so the definition is a bit involved, but one sort of has to remember that this category contains the category of A1 invariant Nisnevich sheaves with transfers. So these are Voevodksky's guys, but also more, also more stuff. So for example, the absolute Keller differentials, sheaf of Keller differentials over Z or over K, Hodge-Witt sheaves, and things like this. Okay, so so objects of this category of reciprocity sheaves are, in a way, sheaves F, such that each section has a bounded ramification, or maybe one should say that each section has a conductor of some level. So just to understand what I mean by this, let's consider the example of F equal to omega 1, so the differentials, and K is some discrete valuation field over small k with uniformizer pi. Then F of K is are the differentials, so omega 1 K over K. And the section here is something like F, a polynomial in pi over pi to the n, d pi. And you can talk about the order of the poles of such a section. Okay, so this is exactly the kind of thing that you would like to do for reciprocity sheaves. Okay, so bounding, saying, so sort of computing, sort of filtering the value that this sheaf F has on things like discrete valuation fields by order of poles. So this is a kind of operation that you can do on differentials in a very natural way. Okay. So what has this to do with our category of log motives? So here I would like to advertise two things. The first is a theorem by Shuji Saito. And so he proved that there exists an exact and fully faithful functor that he denoted log from this category of reciprocity sheaves to our category of sheaves with log transfers for the dividing Nisnevich topology, sending like F to say to F log, and this gadget F log is a strictly box invariant Dini's sheaf, and that moreover, the cohomology of this guy, so the cohomology of this Nisnevich sheaf, can be computed as a Thom in our category. Okay, so it's a Thom in logDM between M of X trivial log structure and F log shift I. Okay, so what is F log for a given F? So for example, it's sort of a reasonable extension. So if F is omega I, is F log is the sheaf of log differentials. Okay, so the log somehow subscript is a superscript, sorry, is a reasonable choice. Okay, and as a consequence of this result, then you get motivic proofs for reduced modulus, okay, of formulas for the cohomology of reciprocity sheaves, like a blow-up formula or projective bundle formula or the Gysin sequence that I just discussed. And sort of for a non-reduced modulus, so Dusson yesterday was mentioning that the theory of motives with modulus deals with thickenings, okay, on the boundary. So you're allowed to consider things like divisors with multiplicity, okay? So in the case of multiplicity 1, which is the log situation, then this embedding theorem by Shuji says that all the formulas that you want to have on the cohomology of these sheaves are actually motivic in the sense that they come from formulas that we proved in our category of log motives. But somehow there are more formulas to prove, okay? So more formulas that you can have for the cohomology of these sheaves when you consider non-reduced modulus. And this is the content of the joint work in progress, almost done, with Kai Ruling and Shuri Saito. And here I want to advertise the fact that there will be a series of lectures by Kai Ruling at CAS in the near future. Okay, so he will certainly say more about this. Okay, so since my time is up, so I will stop here.
Thanks very much. Are there any questions? Any questions? Just shout them out. Well, so at the very end, you seem to be suggesting that the theory of the log sheaves is somehow the tame part in the cycles in the general theory, where you allow higher multiplicities. Is that the correct view, or is it something different? What's going? Why you just get these multiplicity 1 things?
So okay, so I think. Okay, so my understanding is the following. So what we can compute in our category, so the Thom that you can produce in our category. So for example, let's say on this slide, okay, so you have a cohomology of a reciprocity sheaf on X. X is a smooth scheme, so it's an open scheme. Okay, it doesn't have a boundary. So can be f of X can be the sheaf of like least rank 1 analytic sheaves. Okay, so like the dual of the abelianized étale fundamental group, something like this. Okay, so the kind of gadget which comes in classical theory. So what you have here is the full guy, okay, without any information about the ramification filtration.
Okay.
So by taking Thom from, okay, so say that X is embedded into X bar D, okay? So X is the open guy.
Yeah.
We can control M of X empty. By control, I mean that the Thom from this guy into something, so for example, into the reciprocity sheaf, is a cohomology of X. If you take map from X bar D, and X bar is proper, smooth, and so on, okay, then you get somehow only the tame part of the cohomology of X. So in general, these gadgets have filtration, okay? So you will have, so we have something like cohomology of X on F, so X inside X bar as before. Here, I would like to have something like fill D H star X F on the pair X bar D. So this guy is, say, okay. So this is something that you can write as Thom in logDM. Here you have fill D reduced. This is also fine somehow, and you can compute in logDM. But the D reduced, so this is the tame part that you mentioned. Right. Okay. But this is not tame. I mean, this contains everything. What we cannot control at the moment inside logDM are the intermediate steps. So like the filtrations. Okay. So those don't have an interpretation, a motivic interpretation, in the sense that they are not Thom in our category.
I see. I see.
So somehow you have like only the two extreme cases, like the tame part, which is close to the A1 word, and the sort of no boundary condition, no bound on the ramification, which is super far.
Right, right. Okay, well, you have infinitely many steps to fill in then.
Yeah.
Shouldn't be so hard. So there's another question from Ola Sanda. Ola, do you want to just say your question or?
Yeah, okay, so it's written in the chat, but so for normal DM, there is an isomorphism between DM and the derived category of Galois modules. So is there an analogous isomorphism for logDM?
That's the conjecture that I stated before. So if you logDM, well, I mean, at the end of the day, we claim that logDM étale with torsion coefficients prime to the characteristic is equivalent to DM, okay, with torsion coefficients prime to characteristic. But that's a conjecture, okay?
Okay.
Okay.
Thanks.
And there's another question. You can see it in your chat, maybe.
True that the derived category of sheaves knees is equivalent to the subcategory spanned by log schemes with proper underlying schemes. So you mean before a box localization? Is this a question? Like, because this is true after box localization. That's the content of it. Yeah, without box. Okay, no, then it's not true.
Okay.
Sorry, I have a naive question.
Oh. Go ahead, Michael.
I have a naive question. So inside logDM, you have DM, which we know well, and we also have the orthogonal to DM. So what can one? Is there any way to understand orthogonal?
To study the orthogonal of logDM of DM inside logDM, you mean?
Yes. So
that's a very interesting question. I have no idea. So yeah, I don't know.
Okay. So you don't have a gadget to compute morphism inside this thing. Okay, thank you.
Yeah, I don't know. I mean, yeah. So for example, I mean, let's see. One suggestion that I got from a conversation with Kai Ruling some time ago was to sort of use, for example, or to study a weight structure on logDM by filtering the order of the poles, like what you do for well, usually, right, in Hodge cohomology, right? This is what, for example, for the Hodge to Ram spectral sequence, and this would. Yeah, I mean, it would be nice to see if this compares well with the weight structure that you have on DM, and that was studied by, I think, of course by you, but then also by other people in the connection to the Hodge or the RAM realization. So, but for the, which is, this answer is orthogonal to what you asked, but still.
Okay, Piotr Achinger has a question. Maybe you can ask it, Piotr.
Yeah.
Yes. So you mentioned the problem of constructing integral crystalline cohomology on your proper log schemes. So can you say, like, in concrete, say non-motivic terms, what the problem is? Is it the problem of descent for log blowups for this thing, or?
Yeah, it's
because
no. That's, I mean. Yes. So okay. So for a smooth log move scheme, then the realization would be given by the log crystalline realization of the guy.
Yeah.
And well, I mean, I suppose that all the ingredients are there. It's just that we have not written this down. Okay. That this actually factors through, so gives rise to crystalline realization, so to a functor from our category, so that respects like the localization and the topology in the correct way. I mean, I think that the sort of tricky part is the invariance under log modifications. That has to be verified sort of a bit more carefully. Okay. But for the box invariance, for example, well, you compare log crystalline with logarithmic Durham-Witt. Well, Durham-Witt for logarithmic schemes.
And you have Kinner's formula there.
You have that, exactly. So you have a projective bundle formula, and then you can sort of, and then cube invariance, so box invariance should be very easy. I mean, should be a direct consequence of this. And then also Nisnevich excision should be, Nisnevich descent should be easy from this. And probably the only thing to carefully check is the log invariance and the admissible blowups. But these are the ingredients, as you said. I mean, it has to be written down, but that's the idea. Yeah.
Right. Thanks.
Hey, any other questions? Some questions?
You did a log version of cyclic homology. Can you do a log definition of Hochschild homology?
Yes, but still cheap. But okay. So I mean, John Rogness did. So he defined log Hochschild homology for. I think also. I mean, also Olson did it. I mean, I'm not so good in the literature in this area, but certainly like people defined log HH like long before us, and we could give a definition by cheating, sort of by using the Hochschild constant Rosenberg theorem and then just taking Thom into the differentials.
Does this? This is a naive question, but can you make a relation with compact support? Like one way to try to do, I mean, you're sort of missing incoherent sheaves, the compactly supported. So does log tell you these log structures? It reminds me somewhat of compactly supported cohomology, because they're sort of like quotienting out by boundaries at infinity. Is there? Can you connect that?
Not on the top of my head. I mean.
Well, it's too vague.
Yeah, maybe. I mean, I have to think a bit about it. I mean, certainly is.
But it's connected with the log. Well, yeah. Okay.
No, but I mean, I think it's sort of related to the way we construct the Thom motives, Thom spaces, for example, right? That we take this kind of like compactifications, but I cannot give you an answer off the top of my head. Sorry, Kirsten.
Thanks a lot.
So I have a question. What about, not the effective part, the non-effective part? Do you want to get some duality somehow? Is that on the screen, or is that...
Okay, so that's on the to-do list. Okay, so for the non-effective part, the sort of first question is what can we say about cancellation? So do we have a cancellation theorem here? Seems to be hard. So Alberto Merice is working on this. It's so somehow that's the first step. Okay, so get the cancellation, and once you have that, then we have to figure out exactly how to phrase the duality in this setting. So somehow the problem is always that okay, so this is a theory of poles. Okay, so we have something like x comma d, and the d is a boundary which we see as poles, and we would need to formulate properly like a theory of zeros. Does it make sense what I'm saying? So
I think that's what Kirsten was asking. That's why I asked the question. Okay,
so then maybe now I understand better Kirsten's question. Yes, so that's something that we have to understand. We don't know. Well, that's what we have to do. But for example, it's very hard to phrase it in terms of correspondences or in terms of cycles, because because the directions are weird. So this inclusions of this inequalities of divisors which appear in the condition of a log correspondence makes not so much sense if you take non-effective divisors. Mm-hmm. So it's not clear, but this certainly is a very, I mean, it's a central question somehow, but we don't know.
Okay, some other questions?
So Piotr has raised the hand again, or it's a point for?
Piotr, did you raise your hand again?
No, I just didn't lower my hand.
Oh, okay. Lower your hand. There you go. Yeah. Okay, so if there are no other questions, then I think we call it a day and see everyone tomorrow. Thanks for coming, and see you all tomorrow. Bye-bye.